6.5 systems of linear equations. When we have one solution, that means that they're intersecting at a point, and it only has that one solution. We've been working on those all throughout chapter 6. Now we're going to see that when we have two lines and they're parallel, they're not going to intersect at all. That means that there is no solution. And finally, when we have lines that land on top of each other because they're the exact same line, there's going to be infinitely many solutions because one line has landed right on top of another one, and all of the points on those two lines are lining up. Infinitely many solutions. Example 1. What would it look like to have no solution? When I graph these two different equations, they look the same in the beginning. 3x plus 2y equals 10. And then we have 3x plus 2y equals 2. So they're not exactly the same line. But when I do graph them, notice that they are parallel to each other because their slope, rise -3, run 2 for the first one, and then rise -3 and run 2 for the second one. They have the same slopes. They are never going to intersect. That is why this one is a no solution. When I'm graphing, what would no solution look like if I was using a different method? Instead of graphing, we could use the elimination method that we learned about in 6.3. So the graphing method was from 6.1. The elimination method was from 6.3. And once we had our equations all set up, here you can see that they've subtracted this equation to get 3x minus 3x. And then I would have to distribute that negative. So that would also be a negative 2y, 2y minus 2y. So we get 0. And then 10 minus 2 is 8. This is a false statement. So when you get a false statement, it is no solution. This is what it would look like algebraically. I would get an equation that was false for no solution, and this is what it would look like for a graph with no solution. How about infinitely many solutions? What would that look like graphically? I have these two equations. And this one is in standard form, x minus 2y equals -4. So when we're in standard form, we usually use intercepts. When I let y equal 0 and when I let x equal 0, we get intercepts. So when y is 0, -2 times y is 0. And when I cover that up, it says x equals -4. What about when I let x equal 0? Here I'm letting x equal 0, so it goes away. And we're left with a statement that says -2y equals -4. When I divide by -2 and divide by -2, we get a y-intercept of 2. So if I looked at my graph, -4, 0, x is -4, 0, there's that intercept at -4. And then 0, 2, x is 0, and I go up 2, and I can see that that intercept is there as well. Now, when I look at the second equation is in slope-intercept form, y equals mx plus b. And so I would use a different technique for that one. I could say, what is the slope of this equation? The slope is 1/2. What is the y-intercept of this equation? That would be 2. And I could start at 2, and then I could rise and run my slope. If I rise 1 and run 2, there's that point where I would create that line. It's the same line. Here are two different looking equations, and yet it is exactly the same line. So that means there's going to be an infinite number of points on that line. We used intercepts to graph, and the second one was in slope-intercept form. And we use the slope and the y-intercept to graph. Two different graphing techniques that we've learned in Algebra 1. So this is what it would look like when it's on a graph. Well, what would it look like if I used algebra? We have another type of method that we've used. We've also used substitution from 6.2. So let's say that somebody wanted to use the substitution method. We're looking at the two equations from above, and we can see here that y is already isolated. Y equals 1/2 x plus 2. And so what are they doing with the 1/2 x plus 2? They're substituting it in for the y value. So we have x minus 2 times what y equals. And when you simplify all that algebra down, you get a statement that is -4 equals -4. This is a true statement. And when you have a true statement, that means that you're going to have an infinitely many solutions. Again, when I'm graphing and I have parallel lines, I have no solution. When I'm graphing and I have the same equation that lands on top of itself, I have infinitely many solutions. And when I'm graphing and they intersect at one point, that's one solution. And I would write that one solution down. I would give that coordinate for the one solution. When we're doing algebra, the same when we were solving equations earlier in chapter 3, we saw that if we got a false statement, that would mean no solution. When we get a true statement, when we solved equations, it was all real numbers. But here, when we get a true statement, it's going to be infinitely many solutions.